again, but let's talk about some technical things. Let's start with to understand the analog circuit, we have to understand device physics. And to understand the device physics, we have to understand semiconductor materials, which is the fundamental substrate used to make these devices. So we'll start talking about semiconductor materials, and we'll take it from there, and we'll go to device physics, talk about some of the devices, understand it at the level that we need for this course. So again, once again, the device physics that we are going to go through, the device physics primer that we are going to go through the next couple of lectures, is not intended as a device physics course. That will be done in a completely different way. This is just to give you the minimum level that you need to be able to understand the circuits. Okay? So, now, as you all know, semiconductors are the basis for electronic devices nowadays. But what is a semiconductor? What is a semiconductor? It's kind of a bad conductor. It actually turns out it's more of a bad insulator. And we'll see that in a few minutes. So, if you want to explain to someone who's not a technical person, what is a semiconductor? It's really a bad insulator. It's not a bad conductor. And we'll see what the difference is. But now, if you were in a basic physics lab and wanted to tell what is a semiconductor and what is not, how would you do that? Well, one thing is the kind of a crude macroscopic approach. We know that if you take a piece of soap, so we're talking about semiconductors, and we know that if you take a piece of material, and you know this from the high school physics, so if you have a slab of certain material, and you have make a perfect connection on this side and the other side as well, and you will have a certain resistance, right? You can measure the resistance between these two terminals, R. And that resistance, as you know, is proportional to what? It's proportional to the length. Say it's L. And inversely proportional to the area here, A. And the proportionality constant is called resistivity, which is shown with rho. Anyone has Greek heritage here, by the way? Because if you do, you will suffer through the course. The way we butcher it, the way I butcher actually, or most of us butcher your alphabet and how we mispronounce that. I apologize in advance. Be careful with that. But anyway, so here you have rho, which is the resistivity. And what are the units of rho? Rho has units of, the resistivity has units of ohms times meters. Now if you look at the resistivity of different materials, they vary quite a bit. So for instance, aluminum has a resistivity, pure aluminum has a resistivity of the order of 10 to the minus 8 ohm meters. Now, silicon dioxide has a resistivity of 10 to the 14. So there's about 22 orders of magnitude difference between just these two materials. And both of them are very commonly used in integrated circuits. To give you an example. So you can look at this kind of range of resistivities, right? You can say, if I put the resistivity on a straight line, and then say, well, okay, this is rho. And I am down to up to 10 to the minus 5 or so, and these are all meters. We say, well, that's a conductor, right? Or ballpark, and it's kind of a 10 to the 5, 10 to the 4. Again, it's a very arbitrary definition, right? And then if you say, okay, what if I go below that? Well, we become a better and better conductor. There's something, by the way, something else, of course, at the very end of this axis. If it's a log axis, then it will be minus infinity. But here, let's say, which is what? It's a superconductor, of course. That's a different phenomenon. And in that case, you have to be zero, resistivity of 0. But we are not dealing with those at this point in time, but yeah, well, we have that. And then if you want to look at the insulators, anything above 10 to the 4, 10 to the 3, let's say 3 or 4 ohm meters, it's called an insulator. And anything in between could be loosely called a semiconductor. Now, with this definition of semiconductor, not every semiconductor is a useful kind of semiconductor that we can use, but we'll deal with that later. As you can see, this is a very crude way of defining it. It's very somewhat arbitrary, and it's not very useful. So this macroscopic view. So let's see if there's some more profound, better way you can gain understanding of this. And look at the microscopic view. Now, you can look at the microscopic view of semiconductors many, many different levels, right? And there are people who many people who actively work on that every day. That's the research area. There are a lot of people who got their PhD and who get their PhDs in that area. But I'll try to give you a model, the simplest model that captures the essence of the things that you're trying to understand. So in that sense, it's not that I'm giving you the complete picture. I'm giving you the simplest model that still captures the essence. And if you're interested in more detailed models, of course, there are a lot of textbooks and things that you can look at. So let's look at the microscopic view. Now, to understand the microscopic view, we'll start with something that you are probably familiar with, and if you're not, I'm sure you are familiar, you may have to refresh your memory about it. And that's the wave-particle duality. It all starts there. Actually, the only thing I have to kind of postulate or tell you is that a particle really has wave behavior, and you can assign a wavelength to it, which is inversely proportional to its momentum, right? And you can, in fact, assign a wavelength called de Broglie wavelength. Lambda, which is, we said inversely proportional to P, to the momentum, and the proportionality constant happens to be what we call Planck's constant. So this is basically all we need at this point to capture the quantum behavior of things. And we'll start from this and derive everything else. Of course, the electrostatic and all those things are soon too. So what does this tell you? It tells you if you have a particle with momentum P, the higher the momentum, the smaller the wavelength, right? And it tells you the particle behaves like wave. Now, why don't big particles show you a lot of wave behavior? Because their momentum is so large and the wavelength is so small that on all macroscopic levels, you don't see them. They're so close to each other, the wave variations are so close to each other that you can't see it, I mean, loosely speaking. But on microscopic level, this is important. This becomes important. And we'll see why. So to see why, let's start with something that you all heard of, which is the basic model for the hydrogen atom, and one of the most basic Bohr's hydrogen model for the hydrogen atom. So what it is, essentially, is a proton, and you have an electron. And let's say this is the simplistic view. The electron actually rotates around, or goes around the proton in a circular orbit. Very simplistic. Very simplistic. We know it doesn't happen this way. We know there's a probability. But let's say this is the case. Now, what do I need for this orbit to be a stable orbit if this electron is behaving like a wave? Well, you know that this wavelength corresponds to the probability of finding the electron, right? This is the wavelength of the wave function, the quantum mechanical wave function. Now, for this to have a stable orbit, what I need is for this orbit to form a standing wave, right? So what we can do is that, let's say, if this is the wavelength, I want to make sure that it, well, it kind of does. Messed it up. So let's say this wave. So for that to happen, what condition do I need to have? Let's say the radius of the circle is r. What is the condition for this to be a stable orbit? In other words, to form a standing wave, a de Broglie wave standing wave. What? What do I need to have? What is the relationship between this wavelength and the radius that guarantees that this wave, the number of, let's say, this perimeter of the circle, the circumference of the circle, is an integer multiple of the number of wavelengths, right? If that's the case, it comes back in exactly the same way as it started. So it can form a standing wave. So let's write that down. That's it. N times lambda, which is the wavelength, is 2 pi r, which is the circumference of this circle, right? Agree? Very basic, very simple. And of course, I know this means that it's NH over P based on de Broglie wave. So that's one equation, one relationship. And that right there tells you not every orbit is an acceptable stable orbit. They're quantized. Right? N is an integer. Now, what else do I know? What keeps it in place? What keeps this electron in orbit? Very simplistic again, that picture. But what keeps it in place? What keeps it bonded? What is it? Duct tape? Electrostatic. Electrostatic attraction. Now, what can I say about electrostatic attraction? What is the force? The force, other than the thing that holds the universe together and you can use it to move the light signal and all that stuff. But the force here is what? The electrostatic force is 1 over 4 pi epsilon naught times the electronic charge, the charge of the electron times the charge of the nucleus, which is, again, E, divided by r squared. Right? That's the force. Attractive. Now, but I know, again, based on very simple physics, Newton's second law, F equals ma. What is the acceleration? It's a centrifugal force, right? So, and this is centrifugal acceleration, so it's mv squared over r, which I can rewrite again for within the classical picture as p squared. So if I multiply the numerator and denominator by m, I get p squared over mr, right? So that's the force. So I have an equation here relating p squared and r squared and r, and between the two of them, so let me write the other side here, 1 4 pi epsilon e squared r squared. So, and then I can cancel one of the r's. So I can cancel this r with that, right? So this is the other equation. So this is one equation, this is the other. So I have two equations and two unknowns for P and R. I can solve. So let's do that quickly. See what we get. So how do I solve these two equations? So let me rewrite them here quickly. It says 2 pi r nh over P, and the other one says P squared over m is 1 over 4 pi epsilon naught E squared over r. So what's the best way to go about solving this? Maybe I can take this 2 pi r from here and plug it in from that there, right? So I can say this is E squared over 2 epsilon naught. I keep that, I keep the 2 pi r. So it would be 1 over that, so it would be P squared over nh. I'm sorry, not P over nh. And this P cancels that P, so P is m naught E squared over 2 epsilon naught h 1 over n. That's right. NH. Okay? And then I can calculate R quickly from that. I can plug this P into that other one and then get the R. So I get the 2 pi cancel the 2 cancels the 2. I get pi in the denominator. I get epsilon n squared h squared pi m naught e squared. Right? We're messing up like this. Cool.
There's an 8.
I'm sorry?
There's an 8.
So here?
Doesn't have an 8.
8? No, why should I have an 8? This 2, this is in the denominator here, but this is in the denominator, so it goes in the numerator. That 2 cancels that 2. So, I got the P and R. Now what? Well, yeah, fine, but what I'm really interested in, what's the quantity that's very fundamental and I usually look at, it's quite interesting, is the energy. I want to calculate the total energy of this system. First off, do you expect it to be positive or negative? The total energy of this system, the electrostatic energy. The total energy, of course, is positive because it has mass is energy and all that stuff. But the electrostatic, energy of the system.
It's negative because it's bound.
Exactly. It's a bounded system. So it's negative. It should be negative. But let's calculate and see if it's true or not. So the total energy is going to be the sum of the kinetic energy and the potential energy. What is the kinetic energy? 1/2 mv squared, right? So it's mv squared over 2. And what is the potential energy? It's the electrostatic energy, right? Which is negative because it's a product of the two charges. One is positive, one is negative. So it's minus e squared over 4 pi epsilon naught r. And that's the total energy. So let's see. What can I write? I can write this as what? I can rewrite this as p squared over 2m, right? Momentum. Now, how about this one? What can I write this as? This looks awfully similar to that, right? So I can just skip this thing is the same thing. So it's minus p squared over m. So the total energy is minus p squared over 2m. Which I can rewrite as, since I know what p is, I get p squared here, so I get minus m squared e to the 4th divided by, this is the 8 we're talking about, epsilon squared, h squared, n squared. Okay? So there's a whole bunch of constants here. And there's this n, which is an integer. Okay, so what is that constant, first of all? What is it? Oh, wait a second. So this is divided by m. So one of these m's cancel. M not, same. So what is it? What is this energy? Well, let's calculate. I'm sure you know all your constants by now. So let's calculate. What is the mass of the electron? Electronic mass? Any takers? Order of magnitude. Give me an order of magnitude. That's enough.
10 power minus 30 kg.
30. Yeah. Well, I mean, it's 9.1 10 to the minus 31, which is very close to what you just said. So it's 9.1 10 to minus 31. Oops. 31. Okay, so what is the electronic charge?
1.6 into 10 power minus 19.
Exactly. So times that to the power of 4. Oops, I probably should have done that. This is a very basic calculator. So it's 1.6 10 to the minus 16 and 19. Power of 4. You know, I'm going to skip this calculation, but trust me, if you calculate this, this is about, I usually do the calculation, but not on this calculator. I have a better calculator at the class usually. So this becomes 2.17 10 to the minus 18 joules. But let's go through these constants, make sure that you remember them. 9 electronic mass, 9.1 10 to the minus 31, 1.6 10 to the minus 19. What's that epsilon?
8.854 times 10 to the negative 12.
And the units are
I think it's
farads per meter.
Yeah, centimeter to 10 minus 10.
Well, that's per centimeter.
Per centimeter.
But you said minus 12, so that would be farad per meter, which is better to remember. At least we don't have to convert a centimeter to meter. H. I'm asking you because we'll be using these quite a lot. So H times constant. Come on. Yeah. What is it?
6.2 times 10 to the minus 30, minus 32.
Right. Close enough. 6.62 10 to the minus 34. But and the units? Joules times seconds. Remember, h nu is energy, right? Or hf, h times frequency. Frequency is 1 over time. So it has to have units of times joules times second. So that second cancels and you get joules. Okay, so, and that's some number, but you can rewrite it in electron volts. When you rewrite it in electron volts, it becomes a familiar number, minus 13.6 electron volts divided by n squared. So, the point, what's the point of this calculation? So, well, okay, well, fine. So what? Now, the point is that there are discrete energy levels. You can't have any arbitrary energy level. This simple system cannot have multiple energy levels. It will just have limited number of them. So for instance, the lowest energy level, which is for n equals 1, is minus 13.6 eV. The next one is that divided by 4, which is probably around what, 4 point something, right? 4.1 eV. The next one is that divided by another 4, probably around 1 point something eV. And so on and so forth. And then they get closer and closer and closer and closer. And then you get to 0 energy level. And then above that, what energy level do we have? What is the energy level above that? It's, well, above that you can have positive energy, but are they discrete?
No.
No, it's continuous above that. It's not quantized. For positive energy, because it's not a bounded system. An unbounded system can have unlimited number of energy. So it's not that energy is always quantized. The energy is always quantized when the system is bounded. But you have this energy level, so you have this kind of like, let's say, I show it like that. And what it means is that in general, I can have electrons associated with each one of these energies. How many electrons can I have per energy level? Let's say the electrons don't interact with each other for now. And let's say I can balance the number of electrons with the number of protons in the nucleus. Very simplistic. But how many electrons can I have per energy level? 2. Okay, that's right. Why 2?
Positive and negative spin.
Positive and negative spin. Why do I need positive and negative spin? Why can't I have 2 with the same spin?
Fermi's exclusion.
Exactly. Fermi's exclusion principle. So what does Fermi's exclusion principle tell you?
Exactly what you just said.
Well, no, in general terms. In general, what is the general statement of Pauli's exclusion principle?
You know, they have the same values of like SPDF and
Yeah, they can't have the same quantum numbers all along. I mean, they can't be identical in all quantum numbers. They can't. They have to be different in at least one quantum number or one quantum problem. And that's why if they're the same in everything else in terms of location and in terms of energy level, the only other remaining quantum number is the spin, which can have only 2 values, up and down, or positive or negative, 1/2. So you can have 2 energy, and then you can have 2 here in principle, and so on and so forth, if you were to fill it up. Alright? Now, okay, so what? Well, that's fine, so we can have something like that. Now, what if so far I've looked at one of these systems, and I can generalize it, like if I change the nucleus charge to Z times E, then there will be a Z in there and all those things that gets modified. But overall, it's pretty much the same. Now, what if I have another one of these atoms far away, let's say down here, and then okay, the same. And I have electrons. Let's say I have multiple electrons here and there, here and there, and there. Let's say they're far away from each other. So these electrons can have the same energy levels, right? These electrons and those electrons. They will be at the same energy level. Minus 13.6 eV. What if I start bringing these atoms closer to each other? What happens?
the energy bands may overlap.
Well, there's no band so far, right? I mean, there are energy levels. But what will overlap? So they start bringing them closer and closer. What happens? Can I put them right on top of each other? Why not? What would that violate?
Pauli exclusion.
Exactly, Pauli exclusion principle. In what sense would it violate Pauli's exclusion?
You have more than one electron with the same type of spin in each state.
Right, and at the same location.
Right.
Why could I have it in this case? What allowed me to have it in this situation? Why didn't you complain here? I have more than one electron in the same state in every, I mean, in energy and spin. This guy and that guy are the same in every respect, in energy and in spin. Doesn't that violate Pauli's exclusion principle?
They're far apart.
Okay. Does Pauli exclusion principle say for things closer than 1 micron?
They're different orbitals.
No, they're the same orbitals, right? They're 1s orbitals.
But aren't the energy levels due to the electrostatic forces, so wouldn't the range actually be sort of important? Like, if you
What
have
is the
two-
range of electrostatic field?
Well, I mean, like, so for electrons over there, as opposed to those in the atom far away, the forces would be negligible as compared to them.
Okay, negligible is the key word. So in principle, actually these cannot have the same energy level even if they are a universe apart. Okay, what I wanted to see you to understand is that this is a gradual transition. There's no abruptness, there's no one point, 1 micron or 1 nanometer or 1 million miles or something like that this happens. They don't have the same energy level. Anywhere. No two sets of electrons have the same energy level anywhere in the universe. But their difference is so little, so negligible, that you don't care. Right? So that's what Pauli exclusion principle really says. It doesn't have any limit on how far apart they are. But the farther apart they are, the closer the energy levels are. The closer you bring them, the farther apart the energy levels get. So what happens if I bring them close to each other? Let's say now, for the sake of argument, these two are close. I don't want to redraw this. If it were windows, I could cut, paste. It's not. Nothing. So what happens then? Let's say they're close.
I'm going to get more a lot of empty states.
Exactly. So the energy levels split or degenerate into 2 energy levels. So instead of having 1 energy level, well, let me just put 1 next to it. I have to do that for all. So if I had one close, what happens is that I get 2 energy levels really, very close to each other, depending on how close these guys are, of course. But if they're not too close, these are close to each other, and each one of these energy levels captures 2 electrons, right? And that's what happens. That's energy degeneration. So, and that's back splitting. If you look at the spectrum of this thing, the light spectrum, that's what you see. So you see it split. Now, what if I add one more atom? What happens? You get 3 energy levels, and so on and so forth. So, if I have a whole bunch of atoms brought together, close to each other, what happens? Then I get so many different levels, right? So let's say I have a lattice made out of multiple atoms of the same kind, very close to each other. What do I expect to happen? I expect there to be so many energy levels within a range, right? So there will be multiple energy here and multiple ones here, to the extent that at some point there are so many of them that for all practical purposes I can say there's an energy band. Right? There are so many of them that you say, well, this is an energy band. Within this range of energies, I have many, many levels with such and such density of states. So that's why you have energy bands in labs, when you have multiple atoms instead of energy levels, individual levels. Now, let's look at this. There's a picture that actually is helpful in understanding this a little bit more. And that's the picture of what happens when you bring, let's say, carbon atoms from infinity to the vicinity of each other and try to actually form the lattice. So you start from carbon atoms that are far apart, and then you bring them closer to each other. So this is the spacing. This is the carbon atom spacing. And I start with carbon because carbon is a column 4 element, the first column 4 element. And many of the semiconductors we deal with are column 4, so we'll see a lot of similarities in that sense. So what happens? If let's say I have a whole bunch of carbon atoms very far apart from each other. Okay? What can I say about their energy levels? What energy levels do I have? Well, how many electrons does carbon have? What is the atomic number of carbon? 6, right? Carbon 12, carbon 13. So 6 electrons. Right? So what are the energy levels? How many energy levels do I have for a standalone carbon atom? Think about it. Remember your basic chemistry? 1s, 2s, 2p. Right. So 1s, you have the 1s energy level, which takes how many electrons? 2. And then you have 1p.
Now you have 2s and
Two
then
s.
2p, right?
Oh, sorry. Oh, wait, yeah. Sorry. 2s2, which takes two electrons. And then I have the 2p, which takes how many? 6. Well, it has room for 6, but carbon has only 2 left, 2 electrons left. So 2b, 2p2. So there are 2 electrons here. Now, I bring them closer and closer. Yes?
And they both be spin.
Yes, you're right. Because there are 2. There are 3 levels, right? There are 3 energy levels. But now, it's immaterial because once we bring them closer, that's where we are interested, but you're right. So when we bring them closer, what happens? These energy levels start getting degenerate, right? Because there are multiple atoms. So they start getting degenerate, like that, and this starts getting degenerate. And the closer I bring them, the wider the band becomes. So this is a band, this is just film. And at some point, they start overlapping the 2s and 2p. And then, interestingly enough, they separate. So at the carbon lattice spacing, so this is the carbon lattice spacing. What you have 3 bands. This band, still, I guess you could call it the 1s band. And now you have this band that takes, so this used to could take 2n electrons for n atoms, and this takes 6n electrons. Now, when they go through this hybridization process, what you have, in fact, you get 4n here. You have room for 4n and 4n. And just as a side note, do you remember when this process, what kind of orbital was that? It's an sp3, right? The ones that look like this. So now at 0 Kelvin, at absolute 0, when there's no extra energy, no thermal energy, which bands are filled and which bands are empty for the carbon lattice? Well, this is full, this is filled, right? I have 2n electrons here. I have 4n electrons left, right? But this has exactly room for 4n electrons. So this is completely filled. And this is completely empty. So at that energy level, I have a band that's completely full, a band gap, but I don't have any allowed states. And then I have states, but I don't have any electrons to fill them with at 0 Kelvin. All of this at 0 Kelvin. T equals. Now, what does that mean? That means that I have no free electrons here that it can move around. And I have this band just completely filled. So what kind of material is it at 0 Kelvin in terms of conductivity?
Insulator.
It's an insulator, right? Why is it an insulator?
Because there are no electrons in
There are no free electrons in this so-called conduction band, but there are a whole lot of electrons here. Why can't these move? No, well, they are 0 Kelvin, but still it can move, right? I can apply an external field and I can move them. They don't move randomly because they don't have thermal movement at 0 Kelvin. But I can apply an external field. Could I move these? How about these guys? Can they carry any charge from them?
Wouldn't you take a lot of energy to take them out?
Well, why do I need to take them out? That's my question, I guess, right? So it's a good question to ask, but why do I need to take them out? Why can't I move them right there? What is so special about this whole band as opposed to that band?
No empty states.
Okay, right, you're on the right track. And why is that a problem? Just think about it. They have nowhere to go. So I can't have net movement. So if I move one electron from here to there, I have to move another electron back to where it was. Right? So there's no empty state. There's no net movement. It's like the analogy that sometimes used is that imagine you have a tube completely filled with water. Right? And then you have this tube, just completely filled with water, and then it's closed at both ends, and it's tilted. Would any water flow? No. Nothing happens, right? But if it was half empty, the water could flow to one side or the other. Right? There would be net flow of water. I mean, there may be internal movement, but there's no net flow. Okay, fine. So that's 0 Kelvin. We which don't operate a lot of semiconductor devices at 0 Kelvin. We can't get to 0 Kelvin quite. We get very close, but the third law of thermodynamics actually says that we can't get to 0 Kelvin. Okay, so at room temperature, or at temperatures above 0 Kelvin, let's say room temperature, what happens? What is different from that picture? Well, at 0 Kelvin, we had this energy band, which was completely filled. So let's look at this energy, let's look at it at the lattice spacing anyway. So let's look at that at that point, right? Because beyond that, we don't care because there's no real lattice in that point. So at that point, and let's look at just the two upper bands. So you have the conduction band, which is empty. And then you have the so-called valence band, which is completely full. At 0 Kelvin, it's like the picture is like that. And now, if you look at the lattice, it's a 3D diamond lattice for carbon. But I tried to map it to a 2D picture, which is like something like this. So it's a simplistic picture, obviously, but something to fit the blackboard or whiteboard in this case. And so on and so forth. So these are carbon atoms, or it could be, and silicon and germanium, and all column 4 elements have the same structure. So let's say this is silicon. It would be the same thing. The lattice spacing would be different, but carbon and silicon have the same crystal structure. So now, what are these lines? What am I showing here? What happens at 0 Kelvin from a structural perspective, these atoms? They're in the lattice. Let's say they have a perfect crystal. They're all bonded together. What kind of bond is this? What kind of a chemical bond is this? It's a covalent bond, right? It's a covalent bond, and each two of these electrons are forming a covalent bond. Basically, they have opposite spins, and they're forming a covalent bond, and there are 4 bonds, and everything is very stable and happy. This is at 0 Kelvin. Now, I raise the temperature, come to room temperature. What happens?
Some may break.
Yeah, why?
Because the energy that is required, like whatever energy they get, like, I don't know exactly what.
No, it's good. I want you to think. Exactly, that's why I'm asking you these questions. I know the answer. I guess I think I know. But, so, that's good. I mean, I want the thought process. That's what matters, right? The facts you can always get. Right. So, there's thermal energy, right? The lattice has thermal energy, so it means that they're moving randomly. And thermal energy is not uniform. It's not that all particles in the lattice have the same thermal energy. There's a distribution. And we'll talk about that in more detail in a few minutes. But some of the electrons have enough energy, more energy than this barrier, this band gap, this energy gap, right? And when there's enough energy, what happens?
Electrons from the lattice.
You can break one of these bonds, or you can release an electron from here. So you can take an electron. An electron has enough energy to jump this conduction band. Or in other words, you can break one of these bonds and release an electron. Well, let's just keep it color-coded for now. Sorry about that. So there's the electron going up there. This is an electron. And so I'm breaking an electron here, so I have a free electron. Now, when the electron is released, what happens? What is left behind? It's a broken bond, right? But this region of space, is it charged or not? Should it be charged? Think about conservation of charge, right? So it has to be charged exactly by plus E. So what I've left here is a region of space that's positively charged. Now, and let's show it with this kind of red circle here for now. We'll talk about it in a second. So this is plus E. So what happens in this case? Now, if I apply electric field, to this semiconductor, what happens? This electron can move, right? Opposite the direction of the electric field because it's negatively charged. What about this region? Can it move?
Yes.
How can it move?
Other electrons occupy that space.
Exactly. So if I apply electric field in this direction, I can force, this electron can jump back in here, break this bond and form another bond here. And say, where does that get all that energy for? It doesn't need a whole lot of energy to break a bond and form another one. Because the energy difference is 0, in fact, in this case. Right? So it's a very easy process for it to do. So you can basically, by breaking this bond and this electron moving here, you can effectively move this positively charged region here. So it can move too. So you apply electric field to this. So you apply an electric field, let's say, oh, these pens. Oh, this is my invisible pen. Yeah. Okay, so let's say I have electric field in this direction. The electron can move this way, and the hole can move that way. Now, it's just a hole. What is left behind is really like a hole, right? But we can treat it like, kind of like a particle. But it's a different kind of particle. What kind of charge does it have? Positively charged, right? So, what can I do with that? Well, it moves and it carries charge. Because now, unlike before, when you had no free states, so there could be no net movement. Now there isn't, at least in this case, there's one. So you can move charge back and forth by moving this empty space. Now the analogy, again, if I use my water-filled tube analogy, is like this. So let's say you have 2 water-filled tubes. Oh, kind of one. Let's just 2. And originally, the top one was empty and the bottom one was completely full, right? Now if I tilt them, can I move any net amount of water? No. Now if I take a little droplet, a little bit of water from this one, put it in the upper one, right? I have a droplet in the upper one, and I have a bubble in the lower one, right? Now if I tilt this, what happens? The droplet goes this way, where does the bubble go? That way. Both of them carry water from me, when in the same direction. Right? The bubble is going this way, the droplet is going this way, and the bubble going that way means that more water is going this way. Right? So now the droplet is easy to deal with, right? Easier to deal with the electron, right? The motion, the movement of that. Because I'm applying some electrostatic force, it moves, I can track it, and of course I have to deal with the rest of the semiconductor body and all those things, but in general, I can deal with it. More easily. How about the droplet? I'm sorry, how about the bubble? How can I deal with the bubble? How can I analyze its motion, predict its trajectory?